Welcome back to the deep dive. Really glad to be digging into another set of sources you sent over. Today, we're looking at something pretty critical in AI, how to make these incredibly powerful large language model, LLMs, actually efficient enough for everyone to use. We've got articles, notes, some really detailed research paper bits, all pointing towards this project called Zebra Llama. So, our mission today is to unpack what makes it tick, understand the core ideas, and see how it tries to make these giant models more practical.
And it's tackling a really core problem. Your sources lay it out clearly. Standard large transformers, they have these two big technical hurdles. They cost a lot computationally, sure, but maybe even more critical for actually using them is the huge memory they need during inference, specifically for the key value cache, the KV cache.
Ah, the KV cache. Yeah, that comes up a lot. Why is that such a headache based on what you've read here?
Well, it's baked into how transformers work. When they generate text or understand input, they have to keep track of information from previous tokens, these keys and values, in the attention mechanism. And this cache, it just grows and grows with the length of the text you're working with.
Linearly, right. Sounds simple, but I guess not in practice.
Exactly. Linear sounds okay, but when you're talking potentially thousands, even tens of thousands of tokens for long context, that linear growth becomes a massive memory hog. You need serious hardware just to run the model, let alone train it. And on top of that, the attention mechanism itself, the calculation part, that scales quadratically with the sequence length. So computation gets really heavy really fast. Put those together, the memory and the compute demands, and it makes it super tough to deploy these big models widely. Think phones, laptops, or even servers without top-tier GPUs.
Okay, so it's the running cost, the inference memory, that's a huge barrier. And the sources mention something about the training paradigm too, right? That it's not sustainable.
Yeah, exactly. The current way is often, taking these giant models and retraining the models from scratch if you need them for a specific task or different hardware. That's just astronomically expensive energy, time, resources. It's not really a scalable way forward if we want more people to actually use this tech.
Right. So the picture painted is amazing transformer models, but fundamental limits on efficiency and deployment, which brings us finally to Zebra Llama.
Yes, Zebra Llama is positioned as a family of hybrid models. The core idea from your sources is trying to get that transformer level performance, but with way better efficiency. And the real innovation seems to be twofold: the hybrid structure itself, and maybe even more interestingly, this novel post-training approach they use.
Okay, let's break that down. The hybrid architecture first. What's being mixed together here?
It uses two different kinds of building blocks. First, you've got state space models, specifically these Mamba 2 blocks. Now, the huge advantage of Mamba 2, the sources really highlight this, is zero KV cache.
Zero.
Zero, which is incredible for memory, especially with long texts. But there's potential downside sometimes. Pure Mamba models might not quite hit the same performance levels as the best transformers on certain tasks. The other piece is multi-get latent attention, MLA. These layers are kind of like transformer attention, but they use a smart compression technique. They work with a much smaller, compressed version of the attention information instead of the full KV cache, so they drastically reduce the memory needed for attention.
But there's a catch there too.
Yeah, you can't compress indefinitely. Squeeze it too much, and the performance starts to drop. It's a balancing act.
So the architecture isn't just using one or the other, it's about how they're put together.
Precisely. The sources emphasize that Zebra Llama interleaves these Mamba 2 and MLA blocks. They strategically mix them, trying to get the best of both worlds. Mamba's zero cache for some layers, MLA's reduced cache for others, aiming for that sweet spot in high performance with much, much lower memory usage overall.
Okay, combining ideas is smart, but the sources really seem to stress the way Zebra Llama is created, this post-training pipeline, starting from models that already exist instead of training a new hybrid from the ground up. That sounds like a key academic contribution.
Oh, absolutely. This seems to be where a lot of the technical novelty lies, according to the paper excerpts. Instead of that super costly pre-training for a hybrid model, they've figured out a practical, scalable way to build these efficient hybrids by essentially transferring knowledge from existing pre-trained transformers.
Okay, walk us through this pipeline then. The sources mentioned three main stages, each with some clever innovation.
Right. Stage one is weight initialization. The idea here is to take the knowledge stored in the weights of a ready-made transformer and use it to give the Mamba 2 and MLA layers a good starting point. It's not random guessing, it's described as a structured mapping.
Structured mapping, how does that work?
So for the MLA layers, they look at the attention weights in the original transformer, the WQ, WK, WV matrices people might know. They use mathematical tools like singular value decomposition, SVD, okay, which is basically a method to find the most important patterns or components within those big matrices. They use SVD on those original weights to figure out good starting values for the MLA's compressed attention parameters. The sources even mention they adapt this slightly depending on the type of attention the original model used, like if it was standard MHA or the group query attention found in Llama. And for Mamba 2, it's a bit different. They tap into this idea that mathematically, transformers and state space models are related. They're like different languages describing similar processes. So they map parts of the learned attention mechanism, like how keys and values interact, onto the parameters within the Mamba 2 equations. Think of it like translated the transformer's learned rules into the Mamba language. This gives Mamba a much, much better start than just random weights.
Wow. Okay, so they're kind of reverse engineering the transformers function to bootstrap the hybrid components. But that's just the starting point, right? What's next?
Exactly. That leads to stage 2, refined initialization through intermediate layer distillation, or ILD. That structured start is good, but Mamba and attention are still different beasts. So ILD aims to fine-tune those initial weights by making the outputs of the individual Mamba and MLA layers match the outputs of the corresponding layers in the original transformer much more closely. How? They use a standard technique minimizing mean squared error loss between the hybrid layer's output and the original transformer layer's output. The clever part, highlighted in the sources, is that they do this using only a small amount of data. It makes this whole refinement step really lightweight and fast.
And why is this lightweight step so crucial, according to the sources?
It seemed critical for ensuring the hybrid layers really capture the behavior of the original model before they get assembled together. It smooths the transition, preserving that valuable pre-trained knowledge. The paper specifically notes this ILD step is especially important for the Mamba layers, probably because their sequential way of processing is quite different from attention's parallel approach, making the initial mapping maybe less perfect.
Got it. So refined Mamba layers, refined MLA layers, all inheriting knowledge from the original. Now you have to actually build the final hybrid model, deciding which layer goes where. That's stage 3.
That's stage 3, smart layer selection. Now you need to figure out the best arrangement of these MLA and Mamba 2 blocks. Just, throwing them together randomly or based only on that initial mapping quality. That doesn't seem to work optimally. So they use what's called a sensitivity analysis. They basically take a temporary model made entirely of the refined Mamba 2 layers. Then, one by one, they swap out a Mamba 2 layer for its corresponding refined MLA layer and measure how much that swap makes the model's output resemble the original transformer teacher's output.
How do they measure that resemblance?
They use KL divergence, which is a way to measure the difference between probability distributions. So a lower KL divergence means the outputs are more similar. The reduction in KL divergence when swapping in an MLA layer is called a sensitivity gain. It tells them which positions benefit most from having an MLA layer instead of a Mamba 2 layer. Interestingly, the sources note that layers near the beginning and end of the model often show the highest sensitivity.
Okay, so they identify the high impact slots for MLA, but you said just picking the highest sensitivity ones isn't the whole story.
Right, because if you just pick the top, say, 10 most sensitive layers, they might all end up clumped together. You could have the start and end of the model full of MLA, but a long stretch in the middle with only Mamba, which might not be ideal for overall performance. So the SMART strategy adds some rules for a better structure. It's a 3-step thing. 1, terminal preservation. They make sure the most sensitive layers right at the beginning and the very end are selected to be MLA. These seem crucial.
Okay.
2, near uniform intermediate distribution. Then, for the MLA layers they can still afford within their target memory budget, they try to spread them out reasonably evenly between those first and last MLA layers. They even have a ruling about minimum spacing.
Like avoiding big gaps.
Exactly. And 3, maximal sensitivity scores. Among all the possible arrangements that satisfy those first 2 rules, the end layers chosen, the even spacing, they pick the specific combination where the total sensitivity gain of all the chosen MLA layers is the highest.
That sounds very systematic, a very deliberate way to construct the final MADI, balancing individual layer impact with overall structure. So the big question, does this whole intricate pipeline actually deliver in practice? What do the results in the sources show?
Yeah, the results they present are pretty impressive, actually. They seem to validate both the hybrid idea and this whole post-training process. First off, the KV cache reduction is dramatic. The numbers are striking. For a 1 billion parameter model, they cut the cache down to just 3.91% of the original size. That's like a 25x compression. And the sources say they did this while actually slightly improving zero-shot performance.
Wow.
And for the bigger 3B and 8B models, it's similar around 50x and 36x compression while keeping over 97% of the original performance. So it directly hits that huge memory problem we talked about.
Okay, that's a big win. What about the training cost?
That's the other major point linked to the post-training approach. Efficient training. They report needing only about 7 to 11 billion tokens of training data for this whole process. using an 8B parameter model as the teacher.
Which sounds like a lot, but how does it compare?
Well, the sources contrast it with methods that pre-train similar hybrid models from scratch. Those can apparently need trillions of tokens. So ZebraLlama's approach represents something like a 200x to 500x reduction in the training data needed. That's huge.
Okay, massive efficiency gains there, but does it hold up on accuracy against other efficient methods?
Seems so. They report competitive or superior accuracy. On standard benchmarks like LM Harness, both zero shot and few shot, ZebraLlama apparently matches or beats other post-training methods like Mambin Llama or Minitron. They specifically call out beating Minitron 8B in few shot accuracy by about 7%, even though Minitron used way more training data, had a bigger cache, and used a larger teacher model.
Impressive. And does this efficiency translate to speed?
Yes, that's the final piece. Improved inference throughput. The sources include graphs showing ZebraLlama models generating tokens significantly faster per second than methods like Mambin Llama, particularly when generating longer sequences. For context lengths up to 32,000 tokens, they're seeing 2.6x to almost 4x higher throughput.
Okay, those results really do paint a strong picture. The hybrid architecture plus that very clever post-training pipeline seems to deliver on efficiency, both memory and training cost, without really sacrificing performance, and doing it much cheaper than starting over.
And the sources also dive into why it works with some ablation studies, basically experiments, where they turn parts of the method off to see what happens.
Ah, useful. What did those show?
They confirm that doing the structured initialization and the ILD step together is really important. Skipping either hurts performance, especially for getting the Mamba layers right and giving MLA a good foundation. They also showed the smart layer selection really does work better than simpler strategies. That three-step process, prioritizing ends, distributing evenly, then maximizing sensitivity, leads to better models than just picking the most sensitive layers alone.
So the structural rules matter.
Definitely. And they found an interesting trade-off. For a fixed memory budget, you have to balance how many MLA layers you use versus how much you compress each one, its rank, or RKV. It's not just about maximizing compression everywhere. A moderate number of MLA layers with a medium level of compression seems to work best. Oh, and one more thing. The size of the teacher model used for distillation helps, but only up to a point. A bigger teacher is generally better, but if the teacher is vastly larger than the student Zebra-Llama model, the smaller model seems to hit a limit, a capacity gap, where it just can't fully absorb all the complexity.
Okay, so they've clearly achieved a lot and they understand why their specific choices work. Did the sources mention any limitations or next steps?
Yeah, they acknowledged a few things. This work was mostly focused on the Llama family of models as the base. While the post-training itself is efficient, you still need access to a good, large teacher model to do the knowledge transfer, which has its own resource costs. Looking forward, they mentioned wanting to try this pipeline on different types of models, like multimodal ones that handle images and text, or maybe mixture of experts models. They also want to scale ZebraLlama up to larger sizes and explore ways to do this kind of distillation without needing a separate teacher model, which would be a pretty big step.
Sounds like plenty of exciting research ahead, building on what they've done. So, Zebra Llama, based on everything in these sources, really feels like a clever combination of architectural mixing and, maybe more importantly, a really practical post training process. It seems like a significant move towards making these powerful LLMs much more resource friendly by reusing existing knowledge effectively.
Absolutely. It suggests a promising direction, particularly from AMD here, for getting advanced AI working well, even when you don't have unlimited hardware for inference. It shows that smart model design and training strategies can really bridge that gap.
So, maybe a final thought for you, our listener, to ponder after hearing all this. How could approaches like Zebra Llama, focused on efficient post training and hybrid designs, really shift how AI gets developed and used? If we can effectively transfer knowledge from massive models much more cheaply than retraining, does that open the door for smaller teams, researchers with less funding, or even running powerful AI on devices like phones or sensors? What challenges, like maybe the complexity of setting up these pipelines or still needing those initial big teacher models, need to be solved to truly make cutting edge LLMs accessible everywhere? Thanks again for sharing the sources and joining us for this deep dive. Definitely keep thinking about these important questions.